Continuing section 15.2, double integral over general regions, and again another simple region basically. So this is example 3. Find the volume of tetrahedron bounded by the plane x plus 2y plus z equal to 2 and x equal to 2y and x equal to 0 and y equal to 0. So let's try to graph this in 3 dimensions first. And so to find how this plane look like, I would basically intersect it with x, y, and z axis. With x-axis means that y and z are equal to 0. With y-axis means the other two are equal to 0, and so on and so forth. So set these two equal to 0, x is equal to 2 right here, and then x and z equal to 0, y equal to 1, and then again x and y equal to 0 over there. So this plane looks like that basically. X, y, z, right? Now there's another plane that is perpendicular to xy plane because there is no z in there. And so this one looks like, and so x is equal to 2y, basically. X equal to 2y. It goes this way, that way, and it intersects this point. So I'm going to redraw this a little better because that has to connect here, and right now we're in an angle that we cannot see it. So I'm going to erase it a little bit. First of all, give myself a little bit more space for drawing. So drawing these are kind of important. That's why I'm starting at this point. This is y, and let's say x. And so I saw that I'm supposed to connect these two together, sort of, and then I have another one that goes that way, and they meet somewhere down here. And we connect this and this. Everything else is going to be in the background basically, so you can use a little bit of a dashed line in the background. This is dashed and that one is dashed, and so I can see that there is this region down here that is the region of the integration basically. So let's draw that region of integration in xy axis. And what is that region? How did we find this line? By setting z equal to 0, right? And so this is x plus 2y equal to 2 by setting z equal to 0 in there. And that's how we found these 2 points also. And so that's one of them, and this line was obviously x equal to 2y. So x equal to 2y, here x equal to 2y, and then the other one is x equal to 2 minus 2y, and so that's the basically it goes like this. So in here, if I said x equal to 0, y is going to be 1, and going this way. Now this is x-axis, this is y-axis. Let's find the intersection of the two, and by setting x and by setting 2y and 2 minus 2y equal to each other, you get y is equal to 0.5, and then x in that case would be 1. X is equal to 1. So this is 1 and 1 half. Now, which direction is it a simple region? This direction. So the lower bound is y, no, we're solving for x in this case because, no, we're solving for y. So let's see, because here is y equal to, and here is y equal to, and we're in the direction of y. And so y, and so I'm finding it over here. Y was equal to, the lower one is y equal to x half. The upper one is y equal to x minus 2 minus x half, right? And so that's the y. And then let's put the, we're finding the, and I'm going to tell you what the integrand is in 1 minute. So you will have dx, and dx runs from 0 to 1. So that arrow saves my life, because I know that the inner one is in the x direction. So I have to solve, because this was linear, I didn't know which way makes it a function. So I kind of solved for y, because I knew the inner is in the y direction. And so I solve for y, and I get x half and 2 minus x half. So what is the integrand in here? So the integrand is, interestingly enough, is the height of the tetrahedron. How do I know the height? This surface, this plane is going to give me the height. So I have to solve for z. Z is equal to 2 minus x minus 2y, and that would be the height. So 2 minus x minus 2y. And then I can solve this integral. So 0 to 1 dx, and then you solve for, you integrate respect to y to get this. And then you plug in y equal to this and y equal to that in here, and you integrate again. So one part that was important here was to be able to draw some three-dimensional objects, and then to understand how the projection of that three-dimensional object was in xy plane, so you can actually calculate the region in there. And so let me bring up the solution in here. And so solution is going to be, when you simplify, you end up with an integral from 0 to 1 of x squared minus 2x plus 1 dx, and that cleans up to be 1/3. I click here, question 15.2b. Let D be the region shown at right. Which of the following iterated integrals can be used to represent integral, double integral over region D of f of x and y dA? So think about it quickly and come back. So I like to have simple regions. Simple region seems to be happening this way, right? So the inner one should be going from the blue to red, and blue and in the direction, so I have to be able to solve for x. Here should be x as a function of y, and here should be x as a function of, well, this is h1 because that's a lower h2 of y. And then what is remaining is the what is the lower y value? That's that one. And what's the higher y value? That's that one. So I can see that C is the answer. See here, inner with respect to x, outer with respect to y, going from 1 to 3, and functions of y, which is constant with respect to x, and so on and so forth.